things did not stay simple for long. In 1936, Carl Anderson discovered a particle that was identical in every way to the electron except for mass, as it was about 200 times heavier. That discovery led to the famous quip, "Who ordered that?" by I. Rabi. But even more surprises were in store. In 1955, the antiproton was discovered, and in 1956, the neutrino was discovered. And throughout the 1950s, a rather enormous number of different massive particles were discovered with the technology of particle accelerators and detectors. By the end of the 1950s, mankind's knowledge of what the world is made of had again grown to be very complex indeed. This slide shows a portion of the particles that have been discovered using particle accelerators. Over time, the number of such particles became so large that it was termed a particle zoo. It was clear by the early 60s that the number of particles discovered was getting so large that there was likely some underlying pattern that could simplify our view of elementary particle physics. A major step forward in simplifying mankind's view of nature occurred in 1964 when Murray Gell-Mann and George Zweig proposed the quark model. Gell-Mann had used the term quark for the elementary particles, while Zweig had used the term ace. Eventually, the term quark was accepted by the community. In the quark model, hadronic matter is proposed to be built from underlying quarks. Baryons have states that have 3 bound quarks, while mesons are a bound quark-antiquark pair. Leptons were identified as a separate type of matter. As a result, in 1964, simplicity was reestablished. Nature consisted of 3 types of quarks named up, down, and strange, and 4 leptons, which were the electron, the muon, and their 2 associated neutrinos. The initial simplicity of the quark model began to fade into complexity almost immediately. In 1965, Glasgow and Bjorkane proposed a 4th quark, the charm quark, which was discovered by Richter and Ting in 1974. In 1970, Kobayashi and Maskawa theorized that CP violation experimental results could be explained by adding 2 more quarks, and indeed these quarks were discovered by Fermilab researchers. The bottom quark was discovered in 1977, and the top in 1995. Also, over the period between 1974 and 1977, a new lepton, the tau, was discovered at SLAC by a team of collaborators. In addition to the quarks and leptons, force carriers are a central part of today's standard model. In 1979, Glasgow, Weinberg, and Salam proposed the electroweak theory of particle interactions to unify the weak and electromagnetic forces in a single theoretical framework. This work predicted the existence of 3 more particles, which were called the intermediate vector bosons. The weak bosons, called the W and Z, were discovered by a team at CERN led by Carlo Rubbia in 1983. Simone Vandermeer enabled the discovery by leading the development of stochastic cooling of particle beams. Note that the W boson comes in 2 types, one with a positive electric charge and the other negatively charged, while the Z particle has 0 electric charge. Our review of the history of what the world is made of has now reached the point where we can present the presently prevailing view. Here we see a depiction of the standard model for elementary particles as advertised by its proponents. The depiction shows a rather simple set of 16 particles, which includes 6 quarks, 6 leptons, and 4 force carriers. While not as simple as either the earth, fire, wind, and water model, nor the proton, electron, and neutron model, it is true that the standard model does have a certain simplicity, as is shown here. It is also true that the earlier simple models did not include force carriers. But most importantly, the earlier models were not correct, as evidence has shown that there were different elementary substituents to what were once believed to be the elementary substances. So proponents take much pride in the correctness as well as the advertised simplicity of the present standard model. Despite the advertised simplicity of the Standard Model, the model has several problems that leave it rather unsatisfactory from a philosophical point of view. The first additional complication is that the rules used to form particles involve a color charge. It is, of course, perfectly acceptable that nature may employ otherwise identical particles that have one of three color charges, but the downside of this is that it means that there are actually 3 quarks for each one listed on the previous slide. The theory also specifies that there are 8 different gluons to serve as force carriers for the color force. Secondly, each quark and lepton shown on the previous slide has an antimatter counterpart. This too is okay, even necessary, but it means that there are twice as many particles than the number advertised on the previous slide. And beyond this counting sleight of hand, there are additional problems with the Standard Model. Fundamental to the theory is the result that no quark can be isolated. As quarks become separated from their partners, the theory stipulates that the force pulling them back in gets even larger. Before a quark can be freed, the force is so large that the energy associated with it is capable of generating a quark-antiquark pair. And each member of the pair then associates with the fragments of what was being pulled apart, so no quark can ever be isolated. Another problem is that the weak force has no direction. Typical forces, such as the electric, magnetic, and gravitational forces, have both magnitude and direction. They are vector quantities. But the weak force is really a particle exchange phenomena that has no direction associated with it. A last known problem is that there is no satisfactory calculational framework for the Standard Model. There are many good approximation schemes, but the mathematics is not anywhere close to the elegance and accuracy of quantum electrodynamics. This makes it hard to compare experimental results against theory to test the model. For all of these reasons, despite its many successes, it took quite a while for the quark model to gain full acceptance in the physics community. Speakers would go up and present things by saying, in what is now viewed as the standard way of doing things, and eventually they would say, in what is becoming the standard model of our field. The Standard Model was indeed a model that became the standard way of looking at things, but early on everyone was under the belief that something better would soon come along. Here we see a slide that is more honest in its presentation of the existing Standard Model. Shown here are each of the 3 colors of each of the 6 quarks, as well as their antimatter partners. Also shown here are all 6 leptons, along with their antimatter partners. Lastly, all the force carriers are shown here. With this full accounting of particles, it is seen that the Standard Model involves 60 elementary particles. Since there are 18 quarks, 18 antiquarks, 6 leptons, 6 antileptons, and 12 force carriers. While some Standard Model proponents may argue that a red up quark is the same as a blue up quark, the rebuttal of mine is that we certainly don't believe that a positron is the same particle as an electron. Even though a positron is identical to an electron in every aspect except for its electric charge and lepton number, we still recognize that any such difference means that the particles are different particles. Similarly, an up quark with a red charge must be recognized as a different particle than an up quark with a blue charge if we are going to have an honest appraisal of the number of elementary particles in our model. With this honest appraisal, it is clear from the diagram presented here that the Standard Model has reached the point in its development where a simpler underpinning is highly desirable. Of course, there are many good things about the Standard Model. First, it gets everything right. No known experiment is in violation of the Standard Model. And whenever new experiments indicate that something might not quite fit, the Standard Model has exhibited the room for growth needed to accommodate any new experimental results. Mixing angles and renormalization, as well as additional quarks and leptons, have been added to the model over time. The analysis techniques are extremely complex, and it takes a decade or more to master them. A full PhD in physics, as well as postdoctoral training, are usually needed to fully grasp the intricacies of the model. Furthermore, the development of the Standard Model has involved man-centuries of effort by some of the best, brightest, and most trained people around the world. As a result, the Standard Model is a monument to the creativity of man that results in a complete modeling of all known particles and forces. But at this moment, it is also important to note that there were many good things about the music of the spheres model for celestial mechanics as well. First, it got everything right. No known observation of stellar or planetary motions were in violation of its tenets. And whenever new experiments indicated that something might not quite fit, the celestial mechanics model exhibited the room for growth needed to accommodate any new experimental results. Additional spheres were added to the model over time as new observations became verified. The analysis techniques were extremely complex, and it took practitioners of the time a decade or more to fully grasp the intricacies of the model. Furthermore, development of the classical celestial model involved man-centuries of effort by some of the best, brightest, and most trained members of the world. As a result, the classical celestial model was a monument to the creativity of man that resulted in a complete modeling of all known stellar and planetary motions. Please be advised that I am not attempting to mock the Standard Model by comparing it to the medieval and now discredited celestial model. I truly believe that the medieval celestial model was indeed a monumental achievement, and I feel it deserves much more credit than it presently gets. The credit should come because of its attention to detail, its coherent fundamentals, and its mathematically correct and exact derivations that led to explanations of all experimental data. It was indeed an impressive effort. However, Kepler and Copernicus showed us that a much simpler model was possible, and it is my belief that nature is simpler than the Standard Model as well.